Ladies and gentlemen, class recording has started. So, yesterday, we started on section 4.2 and said that there's only one vocabulary word that we introduce in this section, and that is the resultant or the resultant vector. And Elise, you just told us that the resultant vector is the sum of two or more vector quantities. And if we write it out yesterday, we wrote it so it looked something like this. My pen, there we go. A plus B equals C, except this A had a little arrow over it, this B had an arrow over it, and this C had a little arrow over it, right? Indicating that those are vector quantities, right? In order to find the resultant vector, two things that we had to do. What's the first thing we have to do before we find the resultant vector? Luke? Place the vectors head to tail. So, we got to line up our vectors head to tail, meaning that the second vector has to start where the first vector ends, the third vector starts where the second vector ends, etc., 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 on down the road. Okay? So first we line the vectors up head to tail. Then, to draw the resultant vector, how do we do it? Go ahead, Luke.
Draw the vector from the
Or the beginning of the first, straight line to the end of the last one. Okay? Or the tail of the first one to the head of the last one. Okay? That's how we find the resultant vector, or represent the resultant vector. Okay? And we went through a couple of examples. The first example we talked about was this treasure map. Here we have two vectors, right? 5 paces north, 3 paces east. And they're lined up tip to tail, or head to tail, however you want to call it, right? And then the purple vector drawn from the beginning of the first one to the end of the last one, representing the resultant vector. Okay? Good there. Later on in the period, we looked at this picture, figure 4.12a, which I think is on page 2 of your packet, if I remember correctly. If we look at the picture, right? All right, if we look at the picture, A and B are lined up properly. B starts where A ends, okay? And vector C, the purple one, is drawn from the beginning of the first one to the end of the last one. Both of those pictures represent this idea of vector A plus vector B being equal to vector C. Good there? Okay. All right. To illustrate that point, before we get into the details of how we do it, let's look at a couple of example problems. So, if you open up your book to, I believe, page 126. Yes, it is indeed 126. page 126, as part of your homework last night, I asked you to do a couple of problems. These are 2 problems that were part of your homework, so if you did the homework, you can go ahead and pull it out. If not, it's here for us and we'll talk, okay? So, number 22, it says, referring to figure 4.16, which is just above it on, there's 4.16 up on page 126, but the problems are down here. So it says, referring to figure 4.16, is the magnitude of A plus D, or vector A plus vector D, greater, less than, or equal to the magnitude of vector A plus vector E? One thing that I'm going to do today, the program allows me to do a couple of things that you might not be able to do on your paper, or at least completely recreate it. But if you watch, I'll show you what I'm going to do, and then you can, make notes or do whatever you want to do to help you remember these things. Okay? So, here's the first thing I'm going to do. I am going to draw some arrows over the vectors in question. So I'm going to draw a new blue arrow over this blue arrow of A. Same length, just now I'll be able to move it. And then I will draw an arrow here with D. And then, just to distinguish the two, I will draw a yellow arrow here on E. Okay? Good there. First it asked us about vector A plus vector D. Are we ready to find the resultant of vector A plus vector D at this point in time? No. What do we have to do first? Go ahead. That's good. We have to move it so that the tail of D, it lines up with A, right? D has to start where A ends. And right now, they're not oriented properly. Okay? So I'm going to, like I said, you can't do this, but I can. I'm going to take D and move it like this. Okay? Anything wrong with that? You can't. You might have to draw. Well, that's what I have to. That's what you have to do. Is you have to take this and come up with a way that you can remember it. But first thing, Caleb, you understand that they have to be lined up head to tail. Okay. So one thing you can do, right? We can take this. Okay. So Caleb, back to our question. You can't physically move them on the paper, but you can redraw them in a way that you can draw a second picture and go, okay, I'm either going to just move D over to here and just draw it as a second picture, or if you just picture it in your head too, that's another way that might be able to help. Okay. So we moved A and D so that they are in a fashion that we can add them, find the resultant vector, and then we talked about the resultant vector being the one that goes from the tip of the first one to the end, or the beginning of the first one to the end of the last one. Okay? Good there. We're supposed to compare this resultant vector, A plus D, to A plus E, or vector A plus vector E. Are A and E oriented in a way that we can find the resultant vector of them currently? No. So I'm going to take E and move it from here to here. Okay. And then I could also move A, right? So that's my next. Like that? I can't put it here. Okay? Gotcha. I could put it here. Okay? Oh, sorry. It's oriented the same way that this E is, so the arrow goes that way. Okay, so, but I could put them this way. That would be all right. Okay? This, technically, if we wanted to talk about it, wouldn't actually be vector A plus vector E. It would actually be vector E plus vector A. But is the answer any different? Shouldn't be. Okay? So, just to sort of be consistent with the notation of the problem, that's vector A plus vector E. And then that would represent the resultants of those two. This question is asking us specifically about what in those two resultant vectors? The magnitude. So Luke, what do we have to look at when we're looking at purple versus green? The length. So in this case here, which one has a greater magnitude? A plus D, the purple one, as opposed to the green one, which is A plus E. Right? So in this case here, the question being, right, is the magnitude of A plus D greater than, less than, or equal to the magnitude of A plus E? It would be greater than. Okay? Simran, go ahead. Okay, hold on to that question just for, so, Simran, did we change, actually that's the next question, okay? That's 23 actually, we're going to talk about that. But in this case, we haven't changed any of those vectors, right? Moving them around the drawing doesn't change them. As long as they're the same length and they point in the same direction, it's the same vector, okay? Well, hold on 1 second to that, okay? So yeah, let's do 23 and we'll address that question, okay? All right, good here. Okay, let's take and, I'm going to do this on the computer because I can do it a lot faster. This and this. Okay. Question number 23 says, referring to figure 4.16, is the magnitude of B minus C greater than, less than, or equal to the magnitude of B minus F? So again, to help me out here, I'm going to draw a vector here for B, okay, which points up, just like B does in the picture. And then, for this case here, here's vector C that points this way. And then, here's vector F that goes from here to here. Okay, good there? All right. B minus C. We're talking about finding the resultant vector, and Elise, you told us that the resultant vector represents the what about two vectors? The sum, the addition of two vectors. But here, we're subtracting, okay? No problem, we just have to fix a few things, all right? I think we're all probably aware, I hope, at this point, that B minus C would be the same as B plus negative C, yes? Again, act surprised, Luke. So, we're good with that, yes? Okay? But in this case, so Simran, now to address your question from before, right? This is C, the way it's currently drawn. But to answer the question, right, we need negative C. How does C change if we change it from C to negative C? Different direction, right? Or completely opposite direction. Even though this wouldn't be on, like, let's say the x-axis or the y-axis like we talked about in chapter 2 and 3, if we know that we're talking about the opposite of a vector, it needs to point in completely the opposite direction. Okay? Kaylin, here's another thing that you can't do, but you have to, you have to understand it, right? But with this, I can take this one and I can go, that's negative C. Good? Basically, yeah, we just flipped it through the other side. Yeah, it's across the origin if you want to think of it that way. Negative 2, positive 2, however, but yeah, it's the same magnitude, but it points in the opposite direction. Okay? But are B and C aligned properly in order for us to add them? Or sorry, are B and negative C aligned properly for us to add them. They're not lined up tip to tail. So, right, I could bring this here, right? And if I do, I'm kind of off the page, okay? So, no problem. I'll just move it over a little bit because that doesn't change anything about those vectors. Wherever I draw them on the paper, it doesn't change what they are. As long as I don't change how long they are and which way they point, it's the same vector. And then the resultant going from here to here. So that would be B plus negative C. It's asking us to compare it to B minus F, which, right, B minus F is the same as B plus negative F. And so, here's vector F, but we need vector negative F. So we do the same thing just like that. Okay? Good there? And take it from there to there, right? And there's the resultant. And that's B plus negative F. So, to answer the question, which one has a greater magnitude, B minus C or B minus F? B minus F, so B minus C is less than B minus F. Good there. All right. Going back to the idea that the resultant vector represents the sum of two or more vector quantities. Okay. We need a way to determine the magnitude and the direction of that resultant vector. That's what vectors need. We got to have a magnitude, we got to have a direction. So there has to be a way for us to determine that magnitude and the direction. If the two vectors that we are adding just so happen to be perpendicular to each other, like these two, we can determine the magnitude of that vector by doing what? Pythagorean theorem, right? And then we could figure out the direction that the resultant vector is pointing using what? Identities, right? Technically, we'd be using our inverse identities because we got to get the angle, but just similar to what we did in section 4.1, right? Using our trig identities to find the different sides of the triangle, using the angles inside of it, whatever. But if we come across this, right, those are lined up properly, and C is still representing the resultant vector, but we can't use Pythagorean theorem on that triangle, right? So we have to have another way to do it. There's two ways that we can do it. We talked about both methods yesterday. The first method, vectors can be added graphically. What does graphical vector addition require, though? Say again? A bazillion things, but using those bazillion things to do what with our picture? Everything's got to be drawn to scale in order to do it, where the length of those vectors have to accurately represent the magnitude compared to each other, and the angles have to be accurately measured to accurately reflect the direction. If you can draw all of those pictures to scale, you can do it. These pictures are drawn to scale because I use the arrows and everything like that. We have no idea what these arrows actually represent magnitude-wise. I guess I lied. I don't know if these pictures are drawn to scale because I don't know what these arrows are representing magnitude-wise, right? They're good at least, you know, for answering these questions, but we really don't know if they were drawn to scale or not because they don't really are representing anything, okay? So, while that is accurate if done properly, drawing scale diagrams is a pain in the butt. Okay? So, the other way that we talked about doing, and we talked about it briefly at the end, is using the components of the vectors to add it algebraically or mathematically. Okay? So today I want to walk you through an example of that because that's the one we're going to do most often. The example that I'm going to do is again on page 126. And it's question number 26, but you need some information from 25 in order to do it, so I'm going to put both of them up here. Alright, so let's take a look here on page 126 at these two problems. So, 25 says, vector A has a magnitude of 27 meters and points in a direction 32 degrees above the positive x-axis. Vector B has a magnitude of 35 meters and points in a direction 55 degrees below the positive x-axis. Sketch the vectors A, B, and the resultant C. Estimate the magnitude and the direction angle of C from your sketch. So 25 is asking us basically to do graphical vector addition. I'm not going to have you do that because I don't want you to go and get the compasses or the protractors out and the rulers and figure out how we're going to accurately, even though Elise has already had, do you have a protractor out too, Elise? Or? Okay, so even Elise is unprepared to do graphical vector addition. So. All right, so let's talk about 26. 26 says use the component method of vector addition to find the magnitude and the direction angle of vector C, the resultant vector, in problem 25. Okay? So, bear with me. I'm going to walk you through the whole process. I will hopefully connect the dots along the way, but if I don't connect the dots along the way for you, I'll hopefully connect them at the end. Okay? Again, Caitlin, I'm going to do some things up here that you might not be able to reproduce on your paper, but I'll tell you what I think you probably should write down to represent what I'm doing. Okay? All right, so the first thing I'm going to do is draw myself an x-axis and a y-axis. I'd like to point out that my old program would make these lines perfectly straight and horizontal unless I made them not to. So if they don't show up exactly straight and horizontal, sorry. Talk to the people at the district level who got rid of my old program. So. Alright, so it says two vectors. Vector A has a magnitude of 27 meters and points in a direction 32 degrees above the positive x-axis. So I am going to use red to represent vector A. So vector A has a magnitude of 27 meters, points in direction 32 degrees above the positive x-axis. First, before we do this, above the positive x-axis from math class, right? X-axis is the horizontal one, y-axis is the vertical one, yes, right? That is the positive x-axis, right? Because if we do ordered pairs and the x value is positive, that's the way we go, right? Just make sure we're good on that, okay? So it says vector A has a magnitude of 27 meters and points in a direction 32 degrees above the positive x-axis. So, here, here, solid arrow, here's red, Okay? And that representing 27 meters and 32 degrees. Okay? Vector B has magnitude of 35 meters and points in a direction 55 degrees below the positive x-axis. Somebody's brain is on fire. Let's see this. Okay, Brett, go ahead. That's, if they're giving us directions from the positive x-axis, generally, Brett, we're going to think of our vectors as starting at the origin, okay? Now, the next step being, right, these descriptions are relative to the origin of the xy axis, but are they ready to be added at this point in time? Are we ready to find the resultant? No. To find the resultant, a plus b, first we have to align our vectors head to tail, right? So, I'm going to take b and move it there. Actually, here, is one of those things I kind of get a do-over, right? So, I'm going to do this, So I'm just going to dip a little bit more like that. And then I'm going to take it, put it down. Okay? Good? And then there's my resultant. There's my resultant. Okay? Have we made a triangle? Yes. Have we made a right triangle? No. So we can't use Pythagorean theorem on this. We can't use trig identities. So where do we go? The first step at this point is take the two vectors that we're trying to add and find their vector components. Okay? I would recommend, especially at the beginning, not trying to do that on top of this overall picture. Okay? So what I'm going to do is I'm going to start a new page. And on that new page, I am going to draw an x-axis here and a y-axis here and an x-axis here and a y-axis here. Okay? I'm then going to go back to my old page and I'm going to take, oh no, hold on. Okay. I am then going to take this red vector, I'm going to copy it, and I'm going to paste it on this XY axis. Okay? Now, Kayla, well, you can't do that. You could draw it separately. Okay? And then I'm going to take the blue one, copy it, and I'm going to paste it on this XY axis. So those are exactly the same two vectors that I drew on the previous page. Even if you don't draw yours exactly the same, you can still do this. Your drawing might not come out as good as mine's going to come out. Foreshadowing, just so you know, right? That wasn't bragging. That was foreshadowing, right? I'm not, yeah, don't worry, Luke. You'll be, yeah, your brain is just going to go boom at the end of this. All right. We know that this is 27 meters, and this is 32 degrees. This is 35 meters, and this is 55 degrees. In section 4.1, we introduced the idea of components. Components always run along the x-axis and the y-axis to ultimately make up the vector that we're dealing with. So here, this would be my x component of A, and this is my y component of A. Why is it drawing that way? I don't want it to draw that way. I know why. Silly. That's just silly. There we go. Okay? If I wanted to, and I do, I'll label that as AX and AY, as the X component of A and the Y component of A. And then over here, this one has an X component like this, and a Y component like this. And I will label that, hold on a second. And I will label this one B sub X and B sub Y. We learned in section 4.1 what has to be true about our two component vectors. How are they oriented in relation to each other? They are perpendicular to each other. So this has to be a right angle, and this has to be a right angle. On those two triangles, even though we couldn't use Pythagorean theorem and trig identities on this triangle, we can use Pythagorean theorem and trig identities on these two triangles. Find these two sides for each triangle using sine and cosine. Okay? Go. Anybody getting some answers for me here? Yeah. Luke, what do you got? Okay. Is that good? 14.3? Okay. So those are those two components. Anybody do the B ones? Bro, what do you got? 20.1? And everybody good with those? Yeah, technically it would. Krista, let's leave a little bit on here just so we can, because we're going to use these components here in a second, but technically they would be 2 sig days. So. Okay, good here. All right, now, again, you might not be able to do this, but I'm going to show you why I did it, okay? I'm going to do this on the computer real quick because it'll make me faster. All right, here, here. There's my two components for the red one, okay? Here, here. here's my two components for the blue one. Okay? I'm going to get rid of this writing here. Okay. Remember, back in section 4.1, we talked about that the component vectors are basically equivalent to the vector itself. So by finding the size, the component vectors of all of these two vectors, in essence what we have done is we have removed this vector and this vector from the drawing, and we've replaced them with these four component vectors. Good? While it's more steps, are the component vectors aligned properly to find the resultant vector? They're all tip to tail. And the purple still represents the resultant vector because it goes from the beginning of the first one to the end of the last one. Good? All right. Next, let's rearrange a little bit. I'm going to take this one and move it down here. And then I'm going to take this one and move it over here. Okay? Even though I've rearranged, there's still tip to tail. Red to blue to red to blue. Okay? Do we know these two together? First, they're both on the x-axis, and they both point the same way. So what should we do with them? Add them together. Okay? Right, go ahead. Yep. Hold on to the one on the right for just a second. Okay? Let's do this one first. So our x values, our x coordinate, or sorry, our x components, they both point the same direction. So we just add them together. Luke, did you add them together in your calculator? What is it? 43.0? 22.9? Oh, you're right. Sorry about that. Alright, so 43.0. Okay? Now, Brett, on the y-axis, we have two components, but one goes up and the other one goes down. How do we distinguish the up one from the down one? One's positive, one's negative. There's more down than up, right? So we're going to subtract them, but our final answer is going to be negative, right? Yes, no, maybe. Good there? 14.4, is that what it is? Is that what it is? 14.4? Oh, you said it, so it must be true. So, what? Oh, did you do? Come on, people. Do 14.3 minus 28.7. What is it? 14.4, which is what I said, right? But it's not just 14.4, it's actually what? Negative 14.4. Okay? Yep. All right. Did you get my foreshadowing? Yeah. So, we added these two x components together, meaning we basically removed this one and removed this one and replaced them with this one. Then we added this one to this one, taking both of them out. Are you confused? Well, that's why we're practicing it tomorrow. But do you understand where these numbers came from? Okay? But now, hold on. This is the connect the dots part, and I can do it in 30 seconds, okay? Here, right, you have an x component and a y component. What do you know about an x component and a y component? How are they oriented? They're perpendicular to each other. And now we have a triangle. It happens to be a right triangle. And the vector we're looking for is what part of the right triangle? The hypotenuse. So you can use Pythagorean theorem, you can do trig identities to find the magnitude and the direction. What is it, Luke? 45.3. Did you happen to figure out this angle theta? You have to do that because you got to figure out the direction. All right.
That was really climactic.
What?
That was really climactic.
That's what it's all about. That's what it's all about. Yes. But you have to take the inverse tangent